Okay. So it's my pleasure to introduce Malabika Pramanik. She will talk about analysis and geometry of sparse sets.
Hi everyone. First off, I'd like to thank Gleb and Alexei for the invitation. Not just for the invitation to visit your beautiful city and your wonderful university, but for their courage in inviting someone who very clearly does not speak the same language for the most part as you do. So I'd like to talk about a circle of problems that I have been intrigued by for a number of years, and in the process, explain some connections that it has with difference equations or differential equations. But really, I'll try to keep it as elementary as possible. If I neglect to mention some definitions, please do let me know if a particular terminology is not something that you are familiar with. Okay, so there are two kinds of problems that I want to at least mention before specializing to one of them. So one broadly falls under what I call configurations, incest. So exactly does this mean? So here's a prototypical question. So given a large set A, and a class of configurations E, does A contain a configuration from E? So already, you see, there are a number of things that I have deliberately left open-ended. What exactly does large mean? Where is this set E? Where does it live? And what exactly does a class of configurations even mean? Okay. So what large is, it's, as we will see, it's in the eye of the beholder. And there are many notions of largeness which is going to dictate the tenor of the results. The set E could live either in continuum or it could be discrete, or for me, they could live in the integers. And for now, a configuration is really just any class of nice sets. So if you like solutions of equations, it could be that. Solutions of a linear equations, solutions of polynomial equations. If you like patterns, like arithmetic progressions, or let's say an isosceles right triangle, whatever pattern is of interest to you, you could throw this into this class script T and call it a class of configuration. So this is really, when I say a class of configurations, this is really just a synonym for now as a family of sets.
May I ask a question?
Yes,
so,
please.
Can I think of this, Ramsey's theorem or van der Waals theorem as special cases of
That
this?
is going to be my first example.
Okay.
Okay, great, perfect. So you know exactly which way I'm headed. So let's start with some examples. So just for comparison purposes, I'm just going to first do it.
Excuse me.
Yes.
When you say E in the script E, do you mean a subfamily of sets then?
So no, this E is a family of sets.
Right. So,
And this E can be any set that belongs to this family of sets.
so it's the family itself.
Script E is a family.
But-
E is a set.
It's a single set.
A single
A
set.
single set.
Yes.
Oh, so
So
script
I-
E is only one family of sets.
Script E is one family of sets.
Okay.
And I'm going to give you an example so that you can see what this script E in an example could look like. Okay. All right. So let's start with
And
maybe.
family means indexed by something or what?
Right now, I haven't said anything because in the fullest generality, it can be just an arbitrary, potentially infinite, potentially uncountably infinite collection.
No, but the point is that usually a family means it is indexed. But then it doesn't mean that two different index cannot be the same.
That's right.
So,
That's
okay,
right.
That's what you mean. Though.
Yes.
Okay.
Yes, that's exactly right. Okay, so here's an example. So as you were talking about van der Waals theorem just a minute ago, that was Ramsey theory based, and I'm going to talk about maybe a stronger version of van der Waals theorem, which is, let's talk about zimmermans theorem. So this is kind of a gold standard in this field of patterns. So what does it say? So suppose that you have a subset of the natural numbers, let's say, okay, and A has positive upper density. So has positive upper density. So this is going to be my notion of largeness. What does that mean? That simply means that if you look at the proportion of A that's in the first n natural numbers and take the lim sup of this quantity as n goes to infinity, we insist that this proportion must remain positive. So we agree that this is a notion of largeness, right? Okay. Then the conclusion is for every n larger than or equal to 3, A contains an n-term arithmetic progression which I'll call AP for short. And what exactly does that mean? That means there exists this set A plus D, A plus n minus 1D. A and D are natural numbers, so that this is contained inside. Okay. Alternatively, you can simply think of this as an n-tuple, and for generalization purposes, this is often helpful, that we are simply looking for a distinct n-tuple in A, such that, so these xj's solve a system of linear equations there where xj plus 1 minus xj is. Okay. So, as I said, this is sort of a very good example. We have a large set. What exactly are the configurations? The arithmetic progressions are my configurations. So if you want, so to go back to this, what is the script E in this case? Script E here is simply all finite arithmetic progressions. Now,
Okay.
yes, please.
Is there a simple example in which there won't be an infinite arithmetic progression?
In for the case of capital A,
Yes.
there are examples where there is not an easy example, but there are examples of A which has positive upper density, but there is no infinite AB.
But it's complicated.
At least as far as I know, I don't know of a simple example. I could provide a reference probably. Yeah, I think.
This is just of curiosity.
Yes, no. It's a great question. I don't know of an example off the top of a simple one off the top of my head, but I believe that there exist those without infinite ABs. Yeah.
Thank you.
In fact, maybe if we have a chance to chat later, I can describe a construction which might lead to this, okay? But let me not launch into that now. Okay, all right. So, I'll say a little bit as a follow-up and before I migrate over to the continuum. Now, this of course begs the question, sure, as long as we have positive upper density, we have lots of arithmetic progressions. What happens if the set no longer has positive upper density, but is still large in some quantifiable sense? Okay, so if I call this example number 1, then for number 2, so the results are kind of mixed here. So there exists, on one hand, and it's been known for a long time, so there exist sets from 1 to n, so that when you look at, so they are large in the following sense, that their cardinality is larger than n to the 1 minus epsilon for all epsilon positive. Okay. And this is yet an contains no. So that's one. On the other hand, of course, there are famous examples where this is not true. So yet, on the other hand, random sets in the integers
Do you put a link on the AP?
Say that again.
When you say A sub n contains no AP.
Well, if it doesn't contain a 3-term AP, then it contains no AP.
3 terms, you have to 3 terms, right?
Yes, so when I say no AP, this means arithmetic progression of any length. There is no, I mean, for something to be
that's all I want to know.
yeah.
I mean, because you have 2 terms and it's always such a
Yes, that's right.
Those 3. Okay.
That's right. So on the other hand, thin random sets in the integers, and of course primes, contain long arithmetic progressions, and these are quite well-known examples.
May I ask a question about number 2?
Yes, please.
So for all epsilon, so nothing depends on epsilon?
Nothing depends on
On
epsilon?
epsilon here?
No, so this is a sequence of sets. So this n goes off to infinity. Okay. And all I'm trying to say is, so this is just, when you are looking at the cardinality of an, so this delta A that I was trying to, this object that I defined here, delta sub n of A. Now, of course, this has to go to 0, but I'm going to let it go to 0 as slowly as possible. So think of a situation, for example, where delta n of A is like 1 over log n. Do you see?
Do you have to have epsilon there?
So this is sort of an example here where this Is that what you are asking? There is a constant depending on epsilon, and this is for every epsilon because that's how this grows.
So I think the question of Alexei can be restated whether the quantifier for epsilon
Yes.
can be moved in the front.
No.
So where should it stay?
It stays exactly here because this is the sort of an example that I have in mind.
Yes, but in the initial statement. So I was saying that for every epsilon, there exists a constant and a sequence of sets, so that.
No.
No,
Aha,
and
okay.
No.
capital N works for all epsilons.
That's correct.
What?
So there exists a
There is
sequence
an
of.
absolute N
Yeah.
that works for every epsilon.
So
That's what
I
it says.
have a sequence of sets.
So sequence is fixed.
Yes.
I see.
I have a sequence
Okay.
of sets, capital N, and they are sort of the capital N is marching off to infinity.
So
There is
it's
no restriction on the epsilon.
One universal sequence that
One universal
works for every
sequence.
epsilon.
That's right.
But with different constants.
That's
Okay, good.
Okay. Okay. All right. So this is a positive result followed by a negative result in the absence of this assumption, followed by yet another example where for thin sets the answer is positive. Okay. So no clear
What-
picture
actually,
as of
just one
yet.
more.
Yes.
In 2, does it mean that for every capital N,
Yes.
there is a capital N that works for all epsilon?
Yes.
So, okay, for every capital N.
That's right. That's exactly right. Okay. Now, going back to RD. So this is the continuum setting. And let's see what the Zimmermann type results look like in a setup such as this. All right. So maybe the first one, the easiest one to understand, what is large size? A large size for me, at least for the big, let's start off by the easiest scenario where I take a set A on the real line and A has positive Lebesgue measure. So this is going to be my notation for the Lebesgue measure of A. Okay. So I'm just going to prove it to you in about a line or so. Then A contains an affine copy of every finite set. Okay, so what does that mean? That means take any finite set of points P, x1 through xn, okay, i.e. given any finite collection of points P, you can find a translate T and a non-trivial dilate delta, such that when you look at T plus delta P, that's contained in. So what exactly is my class of configurations script A here? These are precisely all the affine copies of a finite set. All right. So I don't know if you have you run into a result like this before? If you haven't, what I'm going to do is maybe just tell you why you ought to believe maybe such a statement and what it relies on, and maybe that will pave the way for the next part of the discussion.
So,
Yes.
so the T plus delta T is called the affine copy of P.
That's right.
Okay.
That's exactly right. So an affine transformation is, on the real line, is a translation and a combination of a translation and a termination. Okay. All right. So how do we go about proving such a thing as this? What sort of technique does this rely on? And I'm going to prove this to keep things simple in the simplest situation of the 3-point set where capital P is simply -1, 0, 1. Okay, so basically these affine copies that I'm talking about here, these are 3-term arithmetic progressions, t minus delta t, t plus delta. Okay, all right. So how does this go? So this unlike Zimmermans' theorem, which needs some very refined tools, this relies on a very standard result called the Lebesgue density theorem. What does Lebesgue density theorem say? It says that, so this is, so what does it say? That it says that almost every point x0 in my Lebesgue measurable set A is the density point. Okay. And what does that mean? That means that all you have to do is to take, this is going to start looking very similar to this whole positive density business. If you look at how much of the interval of length r or of radius r centered around x0 is occupied by A, that proportion converges to 1 as r goes to 0. So the act of having positive Lebesgue measure forces this to happen for almost every point x0 in A. Okay, so this is just a fact that I'm going to take for granted. But what does this have to do with the proof of this fact, this existence of an affine copy? So let's try a proof by contradiction. So suppose not. So suppose there exists an A of positive Lebesgue measure, not containing any 3-term AP. Okay. Then pick a density point x0. What do we know? We know that for every t less than or equal to any r, for every t, that real number that you pick, if you look at x0 minus t and x0 plus t, one of these cannot belong to A. Why? Because x0 is already in A. If both of them were in A, it would contain a 3-term AP. So either x0 minus t is not in A, or x0 plus t is not in A. What does that mean? That means that if you now look at x0 minus r for any r, if you look at x0 minus r to x0 plus r and ask how much of it is in A, well, if this isn't there or this isn't there, then this has to be less than or equal to half of the size of the entire interval, which is r. Because half the measure is being forced to go away. But this contradicts that if r is small enough. Why? Because what this says is that this ratio is bigger than, let's say, 0.99 for small enough r. So on one hand, this is larger than something, 1.98 r, and on the other hand, less than r, so these two things simply don't mesh. Okay. Now, you can take this and just a simple modification of this will work for every finite set. I wonder what you think of the most immediate generalization of this rather simple statement that every finite set is represented inside a Lebesgue measurable set of positive measure. What do you think? what should be the right follow-up question to ask once you have shown that every positive Lebesgue measure set contains a copy of every finite set?
Well, I mean, are you asking about taking higher D's, or are you asking about another notion of large?
That's all of those are viable questions. So, for example, if you take this example, so that is an easy answer to the first question, which is if you take this in RD, there is a Lebesgue density theorem in RD. You simply replace these intervals by balls, and much of what I said carries over. So that's a known statement. Now you could talk about other notions of largeness, or if we could stick with this notion of largeness just for a little while longer and ask ourselves, can we pack in more patterns? Is it possible that we've settled that every finite set is in here? What about infinite sets? Okay, so that's another question. And it turns out that this extremely natural follow-up to this very simple proof is a long-standing open problem. It's called the Erdős similarity problem. And in fact, it's a conjecture. Maybe it's. And what's the conjecture? So the conjecture is given. So his exact statement is that no infinite set so sets that are represented through affine copies inside sets of positive Lebesgue measure are called universal. No infinite set is universal. And what does that mean? I.e., given any infinite E, there exists some A subset of R positive Lebesgue measure such that A does not contain any non-trivial affine copy Now, this remains one of the central problems in geometric measure theory. So, all the work that has gone into this thus far has been in showing that certain infinite sets are non-universal. So,
what are you defining about universal here?
So this is just a nomenclature. So this is the nomenclature which is a set is universal.
Yes.
If every set of positive Lebesgue measure contains a non-trivial affine copy of that set.
So that is
Yeah, this is the definition of
there's
universal.
no.
So this is how.
So
if
this
you just
negative.
look up,
Negative.
that's right.
Yeah,
So if you
That's
just look
negative.
up, this is how usually the Erdős similarity problem is stated.
Ah.
That's why I stated it in the way that it's not the
okay,
most
all right.
popular rendition, and then that's the meaning. Okay, so what's known? So we know, for example, that slowly decaying sequences, like, for example, 1/n, these are non-universal. What's also known is that if you take some sets of certain infinite sets, they are non-universal. What is the conjecture remains open in full generality. For example, it's not known if the simplest geometric sequence 2 to the minus n is universal or not. Okay. All right. Any questions thus far? If not, so I think I've given you some sense of what some of the problems here look like. Maybe what I should do next is to give you a sense of the different notions of size that exist in the literature. Okay, so we ran into a few, density, measure, and so on, but there are many others. How about I just put them on this side of the board and
Sure.
we can refer back to them whenever we need to. There's one easy one, measure. So you put a measure on a set that has larger measure is of course quantifiably larger than a set of smaller measure. Okay. Then there is the notion of dimension, and depends on what sort of dimension are we looking at. So let me talk about maybe 2 today. There's the notion of Hausdorff dimension. So what exactly does this do? So suppose you have a set A sitting inside D-dimensional space, and to keep things simple, let's just assume everything inside is Baroque. So one of many equivalent definitions of the Hausdorff dimension is the following. It's the supremum over all indices alpha, such that there exists a probability measure mu supported on A, such that the mass that mu assigns to any ball centered at x of radius r, and this ball can be arbitrary, it can only grow at a certain prescribed rate. So if you look at the supremum over all x's and all radii alpha, this has got to be 1. Okay? So what this ensures, it might be good to take a moment to understand what exactly this is trying to say. The smaller your A is, the lower this object is going to be. As an extreme scenario, if you think of A being a singleton, so the only probability mass that you can assign to it would be like a Dirac delta, the only possibility for alpha there would have to be 0. Okay? The more spread out the set A is, the larger alpha will be. And of course, this is consistent with our usual notions of dimension. Every line, smooth curve will have Hausdorff dimension 1. Okay? But also, if you think of other objects like the middle third Cantor set, that will have a fractional dimension. So a good example to have in mind is...
But could we get back to singleton? So if I have a singleton, right, so the only measure I can assign is measure supported the singleton with probability 1.
Yes.
So every ball will
Yes.
have measure 1.
Yes.
Well, but then I can take any positive alpha, right? 1 over r to alpha is always less than infinity.
No, because how's that possible? You have to do, this is the supremum over all x. So let's say A is just the point 0.
Mm-hmm.
Take a ball centered at 0 of
Okay.
any radius.
Yeah, it has...
Then this is going to be 1.
Sure.
This object is going to be 1. And if you want that, if you the only possible...
I divide by... Okay, I divide by...
alpha, the only possible value of alpha.
Yeah, sure, okay. Thank
So
you.
if you take the Hausdorff dimension of the middle third Cantor set, that's log 2 over log 3. So On one hand, this assigns a value to sets for which our normal geometric notions of dimension doesn't quite carry over. At the same time, it agrees with all our existing notions of dimension, such as curves and surfaces. We'll have the right dimensions according to this. Okay, so that's one example of size. The other one, also worth keeping in mind, often used in the literature, is something called a Fourier dimension. What does a Fourier dimension do? It has, I want to specify it because it has a representation which is very reminiscent of this, it has many sort of points of similarity with this definition and yet does something different. So the Fourier dimension of A is the supremum over all beta between 0 and D, such that there exists a mu, a probability measured mu, so I won't write it all over again. So as probability measured mu supported on A, such that if you look at the Fourier transform of the measure, that has to grow or decay at a prescribed rate, and the exponent that it is allowed to grow is negative beta over 2. So that's okay. So once again, let's step back and understand what exactly this is trying to do. First of all, it is known that the Fourier dimension is always less than or equal to the Hausdorff dimension. In particular, for the middle third Cantor set, this is 0. On the other hand, if you have, for many sets, especially random sets, they are equal. So what Fourier dimension picks out is in some way more specialized than what Hausdorff dimension does. And therefore, sets with higher Fourier dimension typically have more structure and contain more patterns than a set of large Hausdorff dimension. And there are many examples that substantiate this meta principle. All right. So let's see if you have any thoughts about these questions, about these definitions, but if not, I'll give you a moment. Should we go on there? Mm-hmm. All right. So let's see. So we have some notions of size. We know we have an idea of what the problem is. So let's see what are the kinds of results that are available. So for at least the purpose of today's talk, let's sort of broadly have 2 or 3 categories. So the results of following types. So one could be existence results. So, and what does a typical existence result say? Well, they all follow, if A is large, so this seems to be kind of the motto. If A is large, A must contain many patterns. Now let's see some manifestations of this principle. So an old result of Steinhaus, we often sort of encounter this in analysis textbooks. So it says that if A is a subset of the real line, positive Lebesgue measure, then the difference set A minus A contains an integral. Okay, so this is sort of a very, what shall I say, maybe one of the first results in this area where if you have a large set, you can say something about the structure of that set. That's one. Almost the next result that comes to mind is now a well-known open conjecture with many attempts to crack it. It's called Falconer's distance set problem. And the conjecture says that if A is a subset of Rd, Borel and everything, and its Hausdorff dimension is at least half the ambient dimension, and D here is bigger than or equal to 2. Okay? So this allows for A to have 0 Lebesgue measure, because sets that have positive Lebesgue measure automatically have Hausdorff dimension D. Okay? So if it has at least half the dimension, then if you look at the distance set, so I'm going to write this as delta of A, and this is called the distance set of A. What exactly is it? This is nothing other than all the possible distances between the points in A. The conjecture says that this set must have positive Lebesgue measure. So this has this is as yet open. There has been some very recent developments, but it's still for a long time d over 2 plus 1/3 was what was known. Even now it has come down to 1/4, but it's still open. Okay. Let's talk about some results that are known and yes.
Let me check. So
yes.
A, for example, if D equals 3, right?
Yes, yes.
So A can be a plane in 3D space.
Yes.
But then all different distances. So you look at distances,
Delta
not
of
okay.
distances.
Okay.
This is not the vectors.
It's not
this
vectors.
Is a
It's
subset
numbers.
Of R.
Numbers.
These are
I see.
numbers.
Okay. Thank you. Now
Right.
I see.
So if there are many points, the expectation is we will, by having many points, many distances will be represented. And if the distance of the dimension of A is high enough, then the distance set is going to be large in this sense.
Okay.
Right.
Thank you.
Okay. Okay, so let's talk about maybe one or two more existence results before I go over to a different type, and then I'll circle back again to this. So here's again a prototypical existence result. That's now there are many proponents, but I believe this one that I'm about to quote is due to Greenleaf and Yusevich. So what it says is that here's a large set. So if you look at the dimension of, if you look at a set A, and let's keep things simple, let's just keep it in R2 for now. There is of course an Rn variant, and the dimension of A exceeds 4/3. Okay, so that's my large set. Then if I look at the set T3 of A, and I'll tell you in a moment what that is, has positive. And what exactly is T3 of A? these are all the possible triangles that one can generate from points in A. So this is really the set A cube, A cross A cross A, but modded out by a certain equivalence relation. What's the equivalence relation? You will say that a triplet of points x in A cube is equivalent to another triplet y if the two triangles that they form are congruent. Okay? Where x1, x2, x3 is congruent to y if the triangle of x's is congruent to the triangles generated by y. And by congruent, I mean that you can go from this triangle to that triangle by a combination of translations, rotations, and reflections. Okay.
But how do you define measure? I mean...
Right, that's my next topic. Now, how do you place a measure on a class of triangles? So, if you recall, a triangle up to congruency is always uniquely determined by 3 parameters. And you can decide what these 3 parameters are. This could be the 3 sides, it could be the 2 sides and the interim angle. But you need 3 independent parameters to uniquely determine a triangle up to congruency. And this is positive 3-dimensional Lebesgue measure, hence the number 3. Okay, so this is identifiable with a subset of R3, and it is large in that space, in this sense. All right. Great. So that's one. And what I should do is I'll come back and tell you a few more in this genre in a few minutes, but maybe sort of to put the Greenleaf-Yosevich result in context, let's go over to a different type of results concerning configurations, and I'm going to call that avoidance. How am I doing on time? Okay. So avoidance is pretty much the exact opposite, but it says that if you can have large sets, but these large sets will not contain the patterns that you are looking for. That's the premise here. So there exist large sets avoiding prescribed considerations. Okay. So let's look at some examples. Maybe that will shed some further light on this result, and then I'll say a few more things. Okay. Here's an example. So we talked about right at the beginning how if you take a set of positive Lebesgue measure, it will contain an affine copy of every finite set. That was one of the first things I mentioned. Of course, the natural follow-up to it is that if you let go of the assumption of positive Lebesgue measure, allow sets of 0 Lebesgue measure, but still full Hausdorff dimension, is it possible that such sets continue to contain affine copies of every finite set? So this first result that I'm about to mention negates that. So this is a result due to Keleti. Says that there exists a set A, subset of R, Lebesgue measure 0, of course, but full dimension. Such that A there does not exist any 4-tuple x1, x2, x3, x4 in A with the property that x1 is smaller than x2, x2 could be less than or equal to x3, but strictly smaller than x4, such that they satisfy the equation x2 minus x1 equals x4 minus x3. Incidentally, this is actually stronger than simply saying there will be no 3-term APs. If x2 is equal to x3, that rules out the AP case, but this is normally called one-dimensional parallelograms. So Keleti around 1999 came up with the first construction of this and then made this much more powerful in many different ways later. Okay, so this is a typical avoidance result. And there is also a follow-up result, this is due to Maga, which says that there exists a subset of R2 not containing, so full dimension, so dimension equals 2, not containing the vertices of any isosceles right triangle, or any right triangle for that matter. So let's take a moment just to understand how this stacks up against that. On one hand, the existence result of Greenleaf and Yosevich says that the moment the dimension exceeds 4/3, there are many triangles inside the set A. But Maga says you can actually get a set of full dimension not containing any kind of a right triangle, the vertices of a right triangle, in particular an isosceles right triangle. So there is a takeaway message here. The message being that as long as your set is large, you can be assured that by the containing many points, it already has many patterns. But if you have your heart set on one type of pattern, that may or may not be represented in a set of large size. Okay? All right.
Is there any idea what these sets look like in particular?
These are the sets that are.
Yeah, like the existence of these sets. So we know they exist, but
Yes. So all of these results are constructive. These are not existential results. I'm hoping, let me see how I'm doing on time. I'm hoping that I'll be able to at least give you one construction, maybe Keleti's first construction that gives you a flavor of what goes behind such things. One of my recent results with a student of mine, Rob Fraser, we sort of took some of these ideas and we managed to find large sets that avoid the zeros of countably many functions with very mild regularity conditions. But those are, again, sort of builds off of many of the ideas that already appear here, followed by special geometry of the polynomial functional zeros. Okay, so let's see. I should be trying to stop in like 5 minutes or so, right, Gleb?
Yeah.
Okay. Maybe what I should do.
Maybe more.
Maybe more. Why don't I do this? I wanted to present at least one, the methodology that goes into existence result, the avoidance result. There are other results which say there can be, just as there can be large sets avoiding prescribed configurations, there can be small set containing many configurations, and those are kind of these abundance results. Sometimes sets that are large not only contain many patterns, there is almost an embarrassment of riches in some sense. So those are the other types. Maybe I won't go into that. Instead, why don't I try to present at least one proof in detail, and then if we have room for discussion, we'll talk about that at the end. Okay? All right. So let's talk about Caletti's proof. So what are we trying to do here? Our aim is to find a set of full Hausdorff dimension, but such that it avoids all non-trivial solutions to that equation. Okay. So Caletti's idea was a very elegant twist on the standard Cantor construction. So what do these standard Cantor constructions do? You start off with an interval, you chop it up into pieces, you pick some, you throw away the others. The ones that you throw away, they never ever come back. The ones that you keep, you chop some more, you keep some, and you throw some, and you keep going. So that's the standard Cantor construction. So Caletti's plan was the following. So he starts at step 1. So this is based on a Cantor type construction. But he introduces this new aspect, which is memory. So I call it memory. This is not his nomenclature, but I'll explain why I call it Cantor construction with memory. So in step 1, he starts with A1, which is the interval 0, 1. And at the same time, he starts up what I'm going to call a Q. So what exactly is this Q going to do? At every step, we are going to have a bunch of intervals that makes up my set A sub n, and my Q is going to keep tabs on those intervals. So this is the interval, the first interval at the first step, so my Q has exactly one element. Okay, so nothing has been done. Now, so let's look at step n. Okay. So what we do is, we look at each chosen interval from step n minus 1. Okay. And we are going to decompose it into 6n equal subintervals. And well, if you keep, I'll show you step 2 in a moment. Each one will be of length 6 to the n minus 1 times n factor 1 over. Okay. Now at step n, what we have is, there is at step n minus 1, what we have is a set an minus 1, which has lots of intervals and that we decompose. But we also have a Q. Which is Qn minus 1. And that has lots and lots of intervals in it that I have been. It's a finite list, but it's a very long list. When the time comes at step n to decide which intervals to keep and which intervals to throw, I am going to look at the nth member in this list, which is Jn. It's really important to recognize that this interval Jn appeared in the Cantor construction a long time ago. It was put in the list up there. I'll show you in a moment what this looks like. But here is how you decide, when you take this interval I, that was chosen from the n minus 1th interval, if this I is a subset of Jn,
Excuse me.
yes,
After the J sub n, there's a dot dot dot.
there is a dot dot dot. This is a finite list, but it does end somewhere. I don't know where, somewhere, but it ends somewhere. Yes. So if I is not a subset of Jn, then pick every sixth interval. Subinterval. But if I is a subset of Jn, pick every 6z plus 3. Okay. So I'm going to draw the picture for step 2 so that you see what this looks like. So here's 0 to 1. And at step 1, my only interval was 0 to 1. So at the next step, step 2, so n is 1, so this gets decomposed into 6s, so that's 12 intervals. So this is, let's say, 1 over 12, 2 over 12, and so on, dot, 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 this is 11 over 12. Okay? I have to look at the n minus 1 at them, I'm sorry. So what am I doing? At this stage, everything is contained inside I1 because all the intervals here are subsets of 0 to 1. So we are always in this case. So what does that do? That means I am going to pick 0, 1, 2, 3 over 12, this interval. Okay. And I'm going to pick the next one. Is there anyone, which one's the next? The third one and the ninth one. Does that make sense? Mm-hmm. All right. So this is my A2. And notice what happens to my Q2 now. I start out a Q2. It had the 0, 1, the I1 already. But now I have 2 intervals here. These are my chosen ones. I am going to add them to the queue. So this is my first interval at the second stage. This is my second interval at the second stage. These I have now added. Okay, so this is my J2. This is my J3. Do you see? So now I go on to the next stage. I decompose this further. For the ones at the next stage, I'll be going back and checking if something was a subset of J2, then I select in a certain way. If something is not a subset of J2, which will happen for the descendants here, then I select in a different way. Okay? And this queue leaps ahead much, much faster than the stages can keep up. Okay? So that's why I call it Cantor construction with memory, because the selection mechanism at the nth stage relies on something that appeared long time ago. Yes. Okay, great. So the whole point is, if you just...
What is I here?
Which I?
If I.
This interval I?
Oh, okay. Each chosen I.
So these are the I's, you know, at the next step, when I go to the next step, these are the basic intervals that constitute A2, and those are my I's at the next step.
All right.
So is the construction clear? It's a little bit a complex version of the Cantor construction, but the point is that this does the job, and let's see why. So the set A is nothing other than the intersection of all the ANs, and the claim is that this is on one hand a full Hausdorff dimension, so Y dimension 1. Okay. So there is a rigorous proof, but here is a sort of a proof in the right direction. So if you keep tabs on how many, at the nth stage, the proof that I'm about to show you doesn't prove that it has Hausdorff dimension 1, it shows that it has Minkowski dimension 1, but that's the easier one to convey, so that's what I'll do. Why does it have dimension 1? So you see the number of all possible intervals, intervals at step n this is 6 to the n minus 1 times n factorial, because that's the size of each interval, and the total number of such intervals in 0 to 1 is this much. But what is the number of all chosen intervals at step n? Well, you see, regardless of which situation you are on, you are only choosing intervals that are 6z apart, right? So the number of total that you are going to pick at the nth stage is n factorial. Which means, if you now look at the log of the number of chosen intervals, this is usually the ballpark calculation that you do given with respect to the total number of available intervals. This goes to 1 as n goes to infinity. So please don't take this description too seriously. As I said, this is not a proof of the Hausdorff dimension being 1. It shows us the weaker statement that the Minkowski dimension is 1, but combined with this, it's possible to sort of prove the stronger statement too. Okay. All right. Now, why, maybe the more important thing is, why does it not contain the solution to that equation that I was referring to? Maybe that's the most important part, so let's say a few words about that. So, suppose there exists x1 less than x2 less than x3 less than x4, all in A, such that this equation was satisfied. We need to get a contradiction. Okay. First off, because x1, x2, and x4 are all distinct, and because these intervals, the basic intervals, their length shrinks down to 0, sooner or later, x1 is going to lie in its own basic interval distinct from all these others, right? So since the length of the basic intervals, what are their lengths? Their lengths are precisely these, the ln's. Since ln goes to 0, there exists an n such that x1 belongs to some basic interval at level m, but x2, x3, and x4 don't. Okay? It's at this stage, if you just looked at what happens at this stage, we are not going to get a contradiction. The contradiction is that this basic interval which contains x1 but not the other three, this is going to join my Q at the nth stage. Okay, so Qm, this Imj is going to join here, and somewhere, like many generations later, this is going to dictate how I make my selection. So if this is the capital nth member of the sequence, so if this is the capital nth member in the list, let's see what happens at step n. Let's look at, so x1 is chosen according to the 6z plus 3 rule, and x2, x3, and x4 are chosen according to the 6z rule. Do you see? And now you realize why this can never be satisfied, because one side is of the form 6z and the other one is of the form 6z plus 3 with plus or minus an allowable error. Okay? All right. I think I have said way more than, I would have way longer than what I intended to say, but I've said way less than what I intended to say. But I think I should stop now. Thank you.
Thank you.
Sure. next question about the proof.
Yes.
What's the problem with taking 4 instead of 6?
What's the problem with, in this particular case?
Yeah, like I could take 4 instead of 6, right? And then I will have the same contradiction, right?
That's right, yeah. These numbers, there's nothing sacred about these numbers. This is just what...
Okay.
Yeah.
Okay.
It's
so
important.
nothing
It's
special.
important that at this stage, when you go here, that there is enough of a gap that because you see these are not exact, these are intervals. So even when this is 6z, it's not exactly 6z, it's 6z plus or minus 1 because of this. It's an interval. The interval.
I see. Okay,
So
that
as
might
long,
be.
but there is a lot of leeway for as long as you make sure that even after a plus or minus wiggle room, this is not going. This side cannot equal that side. We are good.
I see. This is why we choose 6, not 4, because there's.
Then we are not
Okay.
going to win the game. But of course, you can choose 10 and
It's even better,
4,
yeah,
and
yeah.
then that's good.
So at the beginning, so you mentioned arithmetic progressions.
Yes.
Are there results about solutions to more general difference equations?
Yes. Well, there are results about many linear equations. There is. If I had maybe another hours to talk about, there is now a whole literature on the existence of solutions of translation invariant linear equations. So what exactly do those look like? They are so you could take an equation of the following form. Let's say a1 x1 plus am xn equals b1 y1 plus bn yn. Okay, and I am going to assume that a1 plus am is equal to b1 plus bn, so that this equation remains invariant under the same translation of the xj's. Okay. Now, there is a very extensive literature available on existence and avoidance results for such systems of such equations. It's really intriguing that there seems to be a natural divide between whether these equations are symmetric or asymmetric. A symmetric one would be where m is n, ai equals bi. That's a symmetric equation. If there is symmetry, then there are certain results that say that you cannot have existence beyond a certain threshold. And then there are other results, there are existence results and avoidance results for such systems of linear equations. I don't know if that was your question.
So could you explain again what does this equation mean? So how should I understand the equation?
It's a system of two, one of them is non-linear, the other is linear.
Yeah, but what are the variables?
The
X's and
variables
Y's?
are the x's and the y's. So these are the coefficients. So xi's, these are the...
So and if I want to specialize to arithmetic progressions, what would that be?
That would be, so x1 plus x3 equals 2x2.
Okay. So I see. So division in x and y's, it's sort of just for notation, and on the line they will be. I see.
So it's
Is there any notation for each
there's some larger picture.
Yes.
I see.
So it's not precisely.
Okay.
It's not just linear. So I think the short answer to your question, it's not just arithmetic progressions at all. It's now...
And how about sequences indexed by two indices?
When you say sequences indexed by two
Like-
indices,
Like
what
an
does that
inti
mean?
square.
Like recurrence relations in which the variables are enumerated by two indices.
Well,
And you can go like...
yeah. So for example, Keleti himself had still on the real line avoidance result where not only does he avoid solutions of these types of equations, which I think in your language these would be sort of parameterized by one index, right? He managed to find an avoidance result where this over that avoids a countable family of prescribed scalars. So I don't know if that actually is not a recurrence relation, but it is a relation that is specified by two independent things. It's not a recurrence relation though, so I don't know what the answer to that is.
And like,
See, a recurrence relation will involve a whole sequence, whereas these are only a finite number, finite set.
yeah, but you can
So get the piece.
and terms piece, right? So because arithmetic progression, it's also a sequence, right? But we say that
No,
we
but it is a
cut-
finite arithmetic progression. He didn't say infinite.
That's
It's
okay.
always finite arithmetic progression.
It's okay.
Yeah,
Yeah.
right? So recurrence is a different game because it's infinite.
So, but can you say something about like if so we were talking about numbers here, right? So if you go next step to functions. So what we can say about
Yes, that was the so that was this result with Robert Fraser and myself that I was intending to that would have been sort of one of the next avoidance results I wanted to talk about. So what we know at the moment is that we take any collection, any countable family of functions. And these functions map, let's say, a V-dimensional space to R. So it's a countable family. Okay. And we want something very mild. So we just ask that we want to make sure that these are not identically zero. And one way we ensure that is to say that there exists some index Kn such that if you look at the derivative, the Knth derivative of Fn, that is non-zero, let's say on 0, 1 to the z. Okay. So the derivative, some finite order derivative is non-vanishing on a given interval.
So this is smooth functions.
These are, right now, at least they need to have this many derivatives.
Ah, okay.
Okay. Okay. So then the conclusion,
So just one of the partial derivatives.
just one of the partial derivatives, that's all we require. Then there exists a set E, subset of R, whose Hausdorff dimension is at least 1 over V minus 1, such that Fn of x1 through xv is non-zero for all distinct x1 through xv. So that's sort of a very general functional statement without assuming linearity or any kind of structure on the functions Fn beyond this mild regularity on the derivatives. So we are trying to avoid the zero set of these countable family of functions simultaneously. We have a similar result for like uncountable families also, but that's in a different direction.
And if I relax this to make Fn's only polynomials, would that make things better?
If-
There are.
Meaning if these were required to be polynomials? Yes. So for example, if you have the same thing, but let's say all your functions were polynomials of degree less than or equal to d, some fixed d, then this can be upgraded to, you can say that you can have this with 1 over v minus 1, of course, but also 1 over d. And depending on how d and v are related to each other, at some times the 1 over d might win out, at certain other times the 1 over v minus 1 would win out. Especially if you have low degree polynomials, the 1 over d is a much better bound than the 1 over v minus 1.
And can you go? even one step further, say that if we have like big enough set of functions, then there will be functions that are, you know, good configurations of functions, so not configurations of
Could
numbers.
you say that one more time?
So
If you have
other results of the form in the set of all functions, if I have a subset of positive density, whatever density could be on functions,
yes.
then there exists, I don't know, function and its derivative simultaneously, for example.
The function and its derivative Okay, let me write something down so that I know what.
Yes, so I'm just trying to state when they run simulated theorem
Yes.
with functions instead of numbers.
Okay, so you
it's
have a collection
not-
of functions,
Yeah.
script f. So these have some functions of some sort. Okay, and
So like my A in the notation of your initial
Yes,
statement, A
yes.
is a set of functions. So it lives in the set of all, let's say, C infinity functions on a line.
okay, it's a set of functions which lives on the class C infinity. Okay, got that.
Yes, and for
Alright.
example, like script E will be a set of, let's say, pairs F and F prime.
F and its derivative f prime.
Yeah, for example.
Okay,
just,
alright, no
and
problem.
it's just a very wild guess, right?
Okay, no problem.
So other results of this form, so that then if A is big in this function space,
Yes.
in whatever measure we choose in function space,
Yes.
then it will contain some set of functions related in this way.
I see. So you're saying that if there is some notion of largeness of this set, which will then guarantee that it will contain something from here.
Yeah.
That's what you're asking.
Yes, and I'm very like.
So
I'm
meaning that
precise.
it will necessarily satisfy a solution of first
Well, it's always
equation,
yeah.
that's what you're saying.
Well, maybe. I mean, I'm free to. I'm just,
Yes.
Yeah, it may be second order, whatever order. So
Okay.
some reasonable relational functions that we encounter in our like everyday life, right?
Right. So off the top of my head, I know of some results which kind of maybe a step in the right direction, but maybe not exactly what you are asking. So there, I mean, I know, I myself have not worked on it, but there are results which say that, let's say, this set is somehow Zariski dense in the set of, if this is a class of polynomials, let's say, then depending on if the coefficients are of some very special algebraic variety given by some relation between the coefficients, some statements have been made about properties of such functions. But that is, but the properties that I know of, that at least the references that I have in mind, they are not like this. They are about certain properties of integrals. Do they hold if you are off of this special set? And then the answer is known to be yes.
Like properties of integrals. Do you mean integrals of these polynomials?
Yes, so they are
Satisfy some-
integrals involving certain polynomials. So these are often sort of called like oscillatory integrals and stuff. So these are objects that look like this. So this chi is fixed, and this phi is free to be chosen in some class. Okay, so so the question is, how does this is an object like this behave as this large parameter lambda gets very large? This sort of oscillates wildly, but what is its size? That's kind of the question. Now, it's known, there are results that say that if you choose your phi wisely so that it doesn't do some bad things, then this has great properties. And often many results that I'm aware of falls into this phi being in a Zariski dense class. But also it is also sadly also true that often the phis of interest fall in the bad set, and then you have to really understand how this means.
In the function case here,
Yes.
the set on the top, must it be infinite?
Which one? This
This
collection of
set. Can I
sets?
have a finite set? Because a finite set won't satisfy the. You know,
Yes.
if you put 0 for the rest,
Of course, yes.
then it won't satisfy the non-zero situation.
No, so if it's quite possible for this to be a finite list and even a singleton. It's completely okay.
Oh, okay.
Yes.
All right.
Right.
All right.
It's not needed that every element in this list be distinct. That's not necessary.
Okay.
And so you also mentioned PDEs.
Yes, I did. I never got to them, did I? Okay. So here's. Do you want to hear maybe like a 2-minute summary of what? Yes. Okay. So this other side of these sparse sets question, so this would be how it's a different, slightly different direction, which says that suppose you have, we know that there are some, we are talking about these different notions of dimensions like thin sets, sparse sets in Euclidean spaces. And one always starts by looking at the things, the geometric things that we love, like curves and surfaces, which have these very geometric notions attached to them. So curves. And there's a tremendous amount of literature about properties that these objects enjoy. So curved surfaces, manifolds, and so on. The question that often is of interest is, do these certain properties of curved surfaces, etc., carry over to generic cases, which have absolutely no differential geometric structure associated to them. And that's where one of the examples that I had in mind comes in. So suppose you have a manifold M comma G, and suppose, just to keep things simple, let's say that M is R2, and you're looking at a differential equation, let's say the Laplacian. So you're looking at the eigenfunctions of the Laplacian. So the Laplacian is now, just as a sort of as a point of reference, one can say that if you look at the these eigenfunctions phi lambda, and then if you take a submanifold of R2, let's say this submanifold could be a curve, let's say a circle on the plane. Okay? If you take these eigenfunctions phi lambda, and if you restrict them to this submanifold, they behave in a certain way, and how you want to quantify that behavior is really up to you. Maybe because I come from a harmonic analysis background, I often look at the Lebesgue norms, so I try to find out how does the LP norm of these objects, how do they grow as a function of lambda, relative to the L2, because these phi lambdas are always L2 normalized. How does this grow when you restrict them? So here's that this is becomes a question sort of in PDEs, and this is a very well studied problem. What is less studied is if you just let go of the assumption that sigma is a smooth curve. If you just say sigma is some arbitrary thin set in the plane, but still has the same Hausdorff dimension as a curve, namely 1, does this nice property still carry over? Certainly the proof doesn't, because the proof uses the Lebesgue measure on the curve very heavily. Then the question becomes, under what assumptions on sigma can you still make such a thing happen, and when can you not? Not sure if that answers your question, Alexei.
What's the significance of the minus sign in the equation of the Laplacian?
Yeah, because you wanted to make sure that when you look at the eigenvalues, they are positive. Now the eigenfunctions, if you look at each the I lambda, then this, if we take two derivatives, this I square contributes the -1, and having a negative sign up front makes sure that after all the cancellation, the multiplication is done, the eigenvalues are non-negative. So this is the positive Laplacian. Nothing would be wrong if I had dropped these.
Right.
It's just the eigenvalues would be negative. That's all.
Any questions? Okay, let's next speaker again.